The next place where we're going to spend some time in this class is dealing with polynomials. And it's actually the next 4 sections in your book that deal with polynomials, but I'm going to break them up into 2 different groups. So in this group, we'll talk about 3.3 and 3.4. And then in the next group, we'll talk about 3.5 and 3.6, where we do more stuff with polynomial functions. And in a minute, I'll define exactly what a polynomial function is, but maybe before I do, I can kind of motivate our need to study these by looking at what we learned in the previous section. So in the previous section, I gave you what's called a quadratic trinomial. Quadratic just means the largest exponent you see is a 2, and trinomial because we have 3 different terms here. And what we learned is that we can rewrite this using this fancy algebraic technique called completing the square into what's commonly referred to as vertex form. And the advantage to having it in vertex form is we can just apply what we know about function transformations to graph it. So the method that we learned was, first we want to group our x squared and our x terms, so maybe subtract 30 from both sides of the equation. And then from here you recognize that our trick only works when the leading coefficient, the number in front of the x squared term, is a 1. So right now it's a 2. To change this into a 1, I'll just divide both sides of the equation by 2. When you're dividing the right side by 2, make sure you divide the coefficients on each of these 2 terms by 2. So this 2x squared changes into 1x squared, and this negative 16x changes into negative 8x. The right side of this equation is not a perfect square, but there is some number that I can add to the right side to make it a perfect square. And what we learned in the previous section is that number is 16, and if I'm going to add 16 to one side of the equation, I better add it to the other side of the equation as well. By adding that 16, I've created a perfect square on the right side of the equation. We learned how to recognize that this is x minus 4 squared. So all that's left for me to do is solve for this y. And I do that by first subtracting 16 from both sides, then getting rid of this 2 by multiplying both sides of the equation by 2. Note that on the right side, that 2 hit each of these 2 terms, so it shows up here and also here. And then finally adding 30 to both sides of the equation, I get as my final answer y equals 2 times x minus 4 squared minus 2, because I have negative 32 plus 30. This standard form is not graphable using our tools, but this vertex form is very graphable. All we have to do is recognize that this 2 and this negative 2 are vertical transformations, and this negative 4 is a horizontal transformation. And so we start out with the graph of y equals x squared, transform it a little bit, and we got our answer. And maybe you're like, okay, right, I kind of remember that from the previous videos. So what are we doing that's new? Well, what we want to do in this section is come up with a graph of this polynomial. Note that these 2 polynomials differ. This one is what's called quadratic, meaning the largest exponent you see is a 2. Over here, I have an exponent of a 3. This is not a trinomial because there's not 3 terms, there's 4 terms. And rather than specify the number of terms, we'll just say polynomial, meaning that there's some terms. So informally, the previous section was kind of devoted to these polynomials where you have an x squared in there. Whereas in this section, it's devoted to polynomials that have more than x squared, x cubed, for example, or x to the 4th power, or x to the 5th power. So how do we come up with the graph of such things? Well, unfortunately, it's going to be pretty difficult, but it'll make it a lot easier if we're kind of speaking the same language. So before I get too deep into how we're actually going to graph this thing, I want to make sure we're comfortable with some vocabulary so I can throw some terms around. So first, these things that we're studying, they're called polynomials. And all a polynomial is a sum of a bunch of terms. So when I say a sum of terms, think we're adding up a bunch of different things. And those things are either just a constant, like a whole number, like the number 30, or a coefficient times x to a positive integer power. Kind of a mouthful, but all I'm saying is right here, what I really have is negative 1 times x to the 3rd power. Right here, I have 10 times x to the 2nd power. Right here I have negative 16 times x to the 1st power. In each case I have some number, negative 1, 10, and negative 16, times x raised up to some power, and that power is what's called a positive integer, meaning it's a whole number and it's not negative. So we won't see x to the negative 5th power, we won't see x to the 7/2 power, nothing like that when we're dealing with polynomials. In this definition, I use the word term and I also use the word coefficient, but maybe those deserve kind of getting defined on their own. All the terms are the things, informally speaking, that we're adding and subtracting to create a polynomial. And all a coefficient is a number out in front of one of these x's. So if you can look at this polynomial and recognize that there's 4 different terms, one of those is a constant term, and for the other 3, my coefficients are negative 1, positive 10, and negative 16 respectively, then you're good on all this vocabulary. One more vocabulary word that I should probably mention is the degree. Degree is a little bit tricky because it kind of has 2 different meanings similar but slightly different depending on the context you use it in. So each term has its own degree, and all the degree of the term is the power that the exponent is raised up to. So this term right here is degree 3. This term right here is degree 2. This term right here is degree 1. And we typically say that constant terms have degree 0. But you don't really have to worry about that. And just like we can talk about the degree of an individual term, we can also talk about the degree of the entire polynomial. And all the degree of the polynomial is the degree of the term that has the largest degree. So what I'm saying is here we have a third degree term, a second degree term, a first degree term, and a 0 degree term. So third degree is the largest degree that I see. Therefore, this polynomial is degree 3. Quadratic trinomials are degree 2 polynomials because their largest term, largest in terms of the exponent that you see, is degree 2. Note that the coefficient, the number out in front of the x's, has nothing to do with the degree. That's totally different. Anyways, that's all the vocabulary words that we'll need as we study these polynomials, so I can finally get to like the gist of this section, which is how do you graph things like this? Like we learned this pretty complicated algebraic technique for how to deal with second degree polynomials. What if we had a third degree polynomial or a fourth or a fifth degree polynomial? Is there some similar technique that's maybe a little bit more difficult that we can learn in our class? Well, no. I mean, if you really wanted the graph, you could always just pull up some graphing program like Desmos and come up with the graph. But the problem is you might not have that handy, and you might want to be able to do this purely algebraically. And also, if we don't understand how to come up with this graph algebraically, we're not going to be able to work backwards. I wouldn't be able to give you this and ask you for the equation that produced this graph. If you're curious, the equation that produced this graph is exactly this one that you see here. Y equals negative x cubed plus 10x squared minus 16x plus 30. Okay, so if we're not using computer software and there's no kind of algebraic technique for us to rewrite this in some form like vertex form where we just come up with different transformations to figure out what the graph looks like, what are we going to do? Well, if I'm being perfectly honest, we're going to kind of estimate our answers, I guess. We're not going to learn a technique to graph these things exactly, so what we're instead going to do is come up with approximate graphs. Rather than produce exactly this graph that you see right here, we'll kind of focus on some of its most important characteristics and learn how to kind of extract those characteristics from the equation. And then when we get really good at that, we'll be able to look at this graph and identify those important characteristics and learn how to go backwards to recreate the equation from those important characteristics. I know that's all a bit vague right now, but the purpose of this video was just to kind of introduce this stuff. I'll get into the nuts and bolts of what we're actually doing in future videos.